Yes, absolutely.
Professor is calibrated in 45 minutes, no problem.
Sorry? Yes. Well, thanks again for the attention. No, that's fine. I'm really sorry for presenting 3 papers. I know it's not interesting for the audience, but it was a coincidence. This paper is not connected to the previous ones. This is a paper that was motivated by a problem, a real problem my group faces when analyzing the structural integrity of some components. I cannot run into many details, but they were components related to pressure vessels. So some of them were manufactured using UOE technique, and some of them using calendered, rolling, it's called calendered. And we needed to assess the effects of the different prestrains on fatigue crack growth and the assessment of leak before break condition. So I'd like to acknowledge Rodrigo and Fabio, which were 2 of my master's students that took part in this development. So, as we all know, several cold forming processes can induce plastic strain into structures. In the interest of this work, we are talking about the UOE technique for manufacturing pipes and some pressure vessels, and the calendering process used for some pressure vessels applications. In our case, these were the 2 methods that we needed to understand better. And the main issue was that this kind of structure presents a non-axisymmetric plastic strain and residual stress distribution that is a result from thermomechanical processing. Gustavo, why did it start? It started because we could not validate some calculations we were doing regarding fatigue crack growth. The values were not coherent. We realized that an extra effect was probably included in the problem, and finally we detected the problem was related to residual stresses measured by X-ray diffraction and the hole drilling method using strain gauges, and then we started studying it in a numerical basis in a more structured manner. Microstructures are thus varying, and we have varying mean stresses and closure effects, and thus the behavior in terms of fatigue crack growth. Here we are studying the fatigue crack growth behavior just to illustrate. The dimensions are not of the real components, but they are illustrative dimensions to show you what happened. So the objectives include assess the effects on an ASTM A35 hot rolled steel. This was the steel used in one of the applications. The others employed API 5L steels, grades X65, X70, and X80. Second, to quantify plastic prestrains caused by the methods, the processing methods, and evaluate the differences on fatigue crack growth rates for different regions in the components. So we use it as a reference Paris law and conventional fatigue crack growth testing under ASTM E647 under mode 1 and K dominance. This is a result that is already published in the literature by Neto et al. 2007, just to show you the effects of increasing plastic prestrain on fatigue crack growth. The literature says that if you increase plastic prestrain, you reduce the ATN in terms of crack growth rate. So it's in thesis, it would be better to have more plastic prestrain if it's under control than having zero or opposite strain. So this is just to show you an example, but they have several limitations. Most papers apply the prestrain directly to CT specimens. So the stress distribution are not uniform. So you have non-uniform residual stresses in every position that the fatigue crack growth will progress. Anisotropy is not considered. they use the concept of accumulated plastic strain. It's not wrong, but we didn't want to use it. And they use no model to describe the fatigue crack growth effects in terms of the material response. So we developed a different technique. We developed some strips. We, first of all, pre-strained the strips to have a uniform strain field. Parallel to that, we also pre-strained CT specimens ready to test, so we had the two conditions. Here I'm presenting the results of the pre-strained strips. We used DIC and also another optical technique to have the reference, and here you can realize along the strips the distribution of plastic pre-straining, 4.3, 8.3, and 14.7%. These were values that were interesting for us in terms of the range that UOE and calendaring imposed in our applications. So it can be, it cannot be extended to other values, but if we need, we can test additional values because we have extra material in our lab. So 3 levels, and the results were corrected for closure. Here you can see some of the DADN versus delta K evolutions. The original is here, the 14.7 pre-strain is here, and using Paris law, we could characterize the effects of plasticity pre-strain level on the ADN, and we could calibrate C and M values using a best fit for a model that is presented here. So one equation for C, one equation for M, and these are the best fits for all the conditions that I'm presenting here. The scatter is a little bit relevant, but I'm not discussing this point here. For the API materials, we developed a set of tests with more samples, so we had a very limited scatter. The material is a half-inch thick ASTM A36. Here is the engineering stress strain curve. Here is the microstructure, ferrite perlite, no banded grains or segregation in these plates. Here is just an example of both models. I won't run into details because you can find in our paper, but we used the dynamic explicit finite element method, plane strain for node elements, the CPE for R. Probably most of you know this element. The models are symmetric. We employed 5 elements on thickness because we detected that with more elements, the strain field did not change anymore. So to save some computational resources, we did it. And the thickness in this case was 24 millimeters. Here is an example of the UOE process. The tools are considered rigid. We simulate this case frictionless, and we consider the contact formulation as discrete. And here's the model for the calendaring process. The numerical procedures that followed were the following. After we simulated and got the pre-strain profiles, we assumed a circumferential through-wall semi-elliptical crack, internal crack, with relative depth A/T ranging from 0 to 1. So the crack started inside and it grew until it reached the outside part of the pipe. API 579 was used for the K calculations, and a MATLAB routine was used to calculate K along the crack front. A fluctuating pressure loading was considered. And the fatigue crack growth was computed using the model I showed you right now for the A36. So we included the C and M solutions in the fatigue crack growth algorithm, and every time that the crack grew, it calculated the ADN at that moment. Just for illustration purposes, these are some examples. First for UOE of the crimping stage, then the U forming here, the O forming, and the expansion, the E forming. And then we could get all the strain profiles. And here we have some examples of the calendaring process, beginning and then all the process happening. We stopped here. We did not complete the full pipe. or pressure vessels because it was not needed. We had everything described here in terms of plastic prestrains, and you can realize the neutral axis here in black. In terms of the prestrain distribution, I will call the attention to something that is important here. These simulations for the ASTM A36 were not supposed to precisely describe the strain field, so it's not so smooth. For the API 5L applications, we used more steps and a more refined mesh to obtain both for UOE and for calendaring the plastic strain fields. So I recommend it is done for every application you need. Here, the trends are the same, but the graphs are not so smooth as it could. So we can realize here, for different angles in the pipe, the varying strain level in terms of percentage of prestrain for the different positions from the inside to the outside. And neutral axis is in the middle. As we can realize, the prestrain is not the same in different positions because the process is not continuous. So this is the critical one, that is the UOE. In calendaring, it's exactly the same along the pipe angles, but in UOE it's completely different, and it's usually employed for pipeline manufacturing. This is an example of DADN, crack growth rate, from the inside of the pipe to the outside in terms of the angle. So you can realize that, sure, if the plastic prestrain is different, if we take different angles for the case of UOE, in some portions, crack growth will be slower, in some portions, crack growth will be a little bit faster. This is just to show you examples. So when we reach the outside of the pipe, in each position, we consider that the leak before break condition was reached. LBB was feasible in all conditions, but we did want to characterize if the crack tip was positioned in every millimeter, what should happen when it reaches the outside portion of the pipe. So I'm bringing only one example of that. This is a graph that shows the number of cycles for the crack to reach the LBB condition depending on the angle position of the crack tip. And you can realize that in some regions we have a larger number of cycles, and in some regions a smaller number of cycles. We should neglect this part because this is the initial contact between the tooling and the model, so it was not so smooth in terms of prestrain distribution. But here we can take into account this behavior, yes, and it's very similar to the other models we developed that were a little bit more refined. So, excluding outliers and these spurious results, the difference between this number of cycles for failure and this number of cycles for failure in terms of LBB are around 60% if we take into account this region. So this is the main point why, in our case, we were not succeeding in validating experimental data. When we started considering such phenomena, the results started to converge, and we had much better coherence. And we consider that such effects should be taken into account, both for design and structural integrity assessment. And I have one extra suggestion. We did not show here the inclusion of triaxiality in the fatigue crack growth calculation, but I suggest that it's also included because we have another investigation running in our lab in which stress triaxiality plays a relevant, remarkable role. So it's a suggestion. Concluding remarks, we could assess fatigue crack growth for the ASTM A36. We had a significant reduction in crack growth rates ranging from 14 to 33% if we consider 4.3 to 14.7% of plastic prestrain. The effects is non-linear. The effects are non-linear with varying delta K. So the greater is delta K, the more pronounced is the effect on plastic prestrain. In our case, as there was a pipe with a relevant thickness, triaxiality was already included, but if you have applications of varying triaxiality, take care. The FE models proved that the plastic prestrains vary with radials and angular positions, and the results I presented here reinforce the need to consider prestrain effects during design of components that are called plastic formed. If you can consider constraint also, it's a good deal, and in real applications, just to give you an idea, we had deviations in the applications that were around 20% to 25%. So it's kind of relevant stuff. Thanks again to our university, and for a scholarship I received for the Brazilian funding agents to Rodrigo Figueiredo. Thank you again, Mr. Chairman.
Thank you, Professor Donato, for these